Okay, so our mission today takes us deep into the heart of a silicon chip. We're looking at something that honestly feels a bit like science fiction becoming fact.
Right.
We're diving into a breakthrough from engineers in Australia, University of South Wales, UNSW. They've managed to get these incredibly clean atomic nuclei to actually talk to each other.
Quantum entanglement, basically.
Exactly. Entanglement happening right inside standard computer chips. It's pretty wild stuff.
It really is.
You know, for the longest time, this whole quantum computing dream felt, well, distant, mostly because of the scaling problem, wouldn't you say?
Oh, absolutely. Building one perfect quantum bit, a qubit, that's achievable. But building hundreds, thousands that work together coherently, that's been the monumental challenge.
Yeah, and this research seems to move the needle on that quite dramatically, actually. It brings a scalable, silicon-based quantum computer, like, much closer to reality.
And it's largely down to the specific materials they chose and, crucially, how they got those materials to interact.
So let's set the stage. To really get why this is such a big deal, we need to understand that core concept you mentioned, quantum entanglement.
Right. Entanglement is, well, it's the key resource. It's what gives quantum computers their potential power over classical ones.
Can you give us a simple version?
Simply put, it's when two separate particles become linked, so deeply linked that they share the same fate. Even if they're separated by some distance, they stop behaving independently.
That weird instantaneous connection, spooky action at a distance, as Einstein called it.
That's the one. And it's that linkage that allows for this potentially massive computational power.
Okay, so our sources break down exactly how this UNSW team achieved that linkage. They used the spins of two atomic nuclei.
Yes, the nuclear spins.
And the key thing for you, the listener, is where they did it and at what scale. They managed this at the manufacturing scale of the silicon chips, probably in the device you're listening on right now.
Precisely. This isn't just, a purely theoretical physics experiment. It's engineering that speaks the language of actual commercial chip fabrication.
But, okay, before we get to the breakthrough itself, we should probably talk about the underlying engineering problem they were wrestling with.
Yes, the fundamental tension. It's something everyone trying to build a quantum computer runs into.
The big quantum catch-22, right?
It really is.
Yeah.
Basically, you have two needs that pull in opposite directions. Need one.
Mm-hmm.
You absolutely must shield your quantum bits, your qubits, from everything. Environmental noise, vibration, heat, stray fields. You need maximum isolation.
Okay, makes sense. Keep them pristine.
Need number two. Those perfectly isolated qubits need to interact with each other. They need to entangle to actually perform computations.
Ah.
That's interaction.
So if they're perfectly isolated, they can't talk to each other to compute.
Exactly. And if you let them interact too easily, the environment just rushes in and destroys the quantum state. Noise kills coherence.
And that fundamental conflict explains why we see so many different approaches, right? Superconducting circuits, trapped ions, photons.
Precisely. Each platform makes different trade-offs between isolation and interaction. Some are fast but noisy, others are quieter but maybe harder to scale or connect.
So where did the UNSW team land on this spectrum?
They chose the nuclear spin of phosphorus atoms, and these atoms were implanted directly into a silicon chip. They really leaned into the quiet, the isolation side of things.
Okay, hold on. Nuclear spin, for someone maybe picturing, the classic Bohr model of an atom with electrons orbiting, what is nuclear spin and why is it considered so quiet?
Good question. Think of the nucleus, the very center of the atom. It has its own intrinsic magnetic property, almost like a tiny, tiny compass needle. That spin direction can store quantum information, your 0 or 1.
Okay.
And the reason it's so clean or quiet is its location. It's buried deep inside the atom, shielded by all the surrounding electrons. It's naturally very well isolated from external magnetic and electric noise compared to, say, the electron spin.
So it's like it's naturally in its own little soundproof booth already.
Kind of, yeah. In fact, CNT professor Andrea Morello from the team described it as, and I'm quoting here, the cleanest, most isolated quantum object one can find in the solid state.
Wow.
And they backed that up. His group previously showed they could hold quantum information in these nuclear spins, maintain coherence for over 30 seconds.
30 seconds. Wait, we need to pause there. That sounds short in normal life, but in the quantum world, isn't that basically an eternity?
It absolutely is.
For
Most quantum systems lose their information in microseconds, maybe milliseconds if you're lucky. 30 seconds is phenomenal. It gives you a huge amount of time to perform operations before the state decoheres.
Which is massive for error correction down the line, I imagine.
Exactly. And they'd also shown they could do quantum logic gates with less than 1% error. So
Yeah.
you have this incredibly stable, high-fidelity qubit. Amazing foundation.
But there had to be a catch, right? The too quiet problem.
That was the massive hurdle. The very isolation that made the nuclei so perfect also made them incredibly difficult to connect together into a larger processor. They were almost too isolated.
They couldn't easily talk to their neighbors. What was the actual physical limitation?
It came down to proximity and, well, shared resources. Before this breakthrough, the only established way to get multiple nuclei to talk coherently was if they were positioned extremely close together.
Okay.
And, this is the key part, they had to be effectively controlled by one and the same electron. That single electron acted as the necessary intermediary, the translator between them.
Right, I remember reading about that limitation. Dr. Holly Stump had a great metaphor for this, the soundproof room.
Yes, that's a perfect analogy she used. Imagine the nuclei are people. They can have super clear, high-fidelity conversations, low error rates, long coherence. But only if they're all crammed into the same tiny soundproof room with that single electron acting as the moderator or translator for everyone in that room.
Okay, I see. The conversation is perfect, but the room is tiny.
Exactly. The electron's influence only extends so far, and you can only pack so many nuclei close enough to share that single electron mediator. As Dr. Stemp pointed out, that model just fundamentally doesn't scale up. You can't build a big computer by cramming everyone into one tiny room.
So the challenge was keep the amazing clarity of the conversation, keep the isolation of the individuals, but get them out of that single crowded room. Give them range.
Precisely. They needed a way for nucleus A to talk to nucleus B
Yeah.
without needing to be right next to each other and sharing the exact same electron mediator.
They needed quantum telephones.
That's a great way to put it. And interestingly, the telephones they engineered also involved electrons, but in a different way. Separate electrons.
Okay, now we're getting to the core breakthrough. How did they use separate electrons to bridge the gap?
So the mechanism, as described by Mark van Blankenstein in the research, relies on a bit of that quantum weirdness again. Instead of nucleus A, nucleus B both being coupled to the same electron C, you have nucleus A coupled to electron 1 and nucleus B coupled to electron 2, two separate nucleus-electron pairs.
Okay, two pairs. How do they connect?
They engineer things so that electron 1 and electron 2 can interact or touch each other across a distance. Now, touch here doesn't mean physical collision like billiard balls.
Yeah, quantum touching is usually different, isn't it?
It is. It's about their wave-like nature. Electrons aren't just points. They exist as probability clouds. They're spread out. If you arrange things so the probability cloud of electron 1 significantly overlaps with the probability cloud of electron 2.
Like ripples interfering on a pond.
Exactly like that. That overlap, that interference, creates a quantum link, a bridge between the two electrons. And since nucleus A is already talking to electron 1 and nucleus B is talking to electron 2, when you link electron 1 and electron 2,
You effectively link nucleus A and nucleus B through that electron bridge remotely.
here you go. You achieve entanglement between the nuclei without them needing to be huddled together under the same electron.
That is genuinely clever. You keep the individual stability of the nuclear spin, that 30-second coherence, but you gain the range by mediating the connection through these overlapping but separate electron wave functions.
That's the essence of it. They turn the scaling problem from one of impossible physical density to a much more manageable engineering challenge of controlling electron wave function overlap. The nuclei stay clean and isolated individually, but now they can interact over distances relevant to actual chip manufacturing.
Okay, so let's get concrete. You mentioned range. What distance did they actually manage to bridge between these entangled nuclei?
The distance reported was about 20 nanometers.
20 nanometers. Okay, my brain immediately says that's tiny, which it is, obviously, 100,000th of a millimeter, roughly.
Incredibly tiny in absolute terms.
But they provided that analogy to grasp the relative scale in the quantum world, didn't they? The Sydney to Boston one.
Ah, yes, that really puts it in perspective. If you imagine scaling up each atomic nucleus to the size of a person,
Okay, a person-sized nucleus.
then that 20 nanometer separation between them would be roughly equivalent to the distance between Sydney, Australia, and Boston, USA.
Whoa. Okay. So, relatively speaking, for these incredibly isolated quantum objects, that's like bridging continents inside the chip. It's a huge leap in communication range.
It really highlights how localized the previous interaction method was and how much range this new technique unlocks.
But here's the absolute kicker, the so what. For anyone interested in practical quantum computing, that 20 nanometer figure isn't just some random number they landed on.
Not at all. This is where the physics meets the silicon industry head-on. 20 nanometers happens to be right in the ballpark the exact scale, really at which features are routinely manufactured on modern silicon computer chips.
The chips made using standard CMOS processes, the ones in our phones, laptops,
The
servers.
very same. So they didn't just demonstrate entanglement, they demonstrated it at a distant scale that is directly compatible with existing high-volume commercial microchip manufacturing techniques.
Why is that compatibility with existing silicon fabs so revolutionary? Why not just invent a whole new manufacturing process?
Money and time, fundamentally. The world has invested, what, trillions of dollars over 50-plus years building up this incredibly sophisticated global infrastructure for silicon chip manufacturing, the fabs, the supply chains, the expertise.
Right, it's enormous.
If building large-scale quantum computers
Yeah.
required completely different exotic materials or entirely new kinds of factories, maybe needing, specialized cooling systems only found in research labs, the cost and time to reach mass production would be astronomical, potentially prohibitive.
But this suggests
This suggests that the path to massive quantum processors might not involve abandoning all that existing silicon infrastructure. Instead, it could involve adapting it, leveraging the immense manufacturing capability we already have. That's a potential shortcut worth, well, potentially trillions.
it completely changes the economics and the timeline for scaling up. And achieving this kind of precision, working at that scale with these materials, clearly wasn't a solo effort.
No, the sources emphasize